And I think the next topic is extremely related. So these presentations connect with each other. The next presenter is Jianghui Geng from Wuhan University. The title of his presentation is Multi-GNSS clock combinations on the repro3 using their combination software.
All right.
And Jianghui, you have the virtual floor.
Okay, can you hear me? You can see my slide,
Yes.
right?
Not
okay,
yet.
Great. Not yet?
Not yet.
Let's see. Oh, yeah, that should share my screen. All right. Okay. I forgot it.
And now we can see your screen. Thank you.
Okay, thank you. Thanks for the invitation on this talk. And hello everyone. So I'm going to talk about more on the clock combination. Just follow the talk by Simon. So we use a software to combine the multi-GNSS clock for no matter whether it's a Lexi clock or integer clocks. All right, so now we have the combination orbits from Salim in the reprocessing, and we have IGS1 and IGS2, which are divided according to their weighting strategies. The first one is the AC specific weighting. That means you have a global weighting, and the second one is based on the specific satellites. So each satellite will have a different weighting strategy. So we will compare them here briefly, and then we, after we have the orbits combination, we also needed to combine the satellite clocks and the phase biases to make the best agreement among the three products to enable the highest performance for the PPP solutions. And here we collect the products from 6 ACs, including the orbit clocks. And we just used the orbit combination results from Salim. So we just show them here. And we have phase biases products from four of them. And we have quaternions, the new IGS products to describe the satellite attitudes over the past 20 or 30 years. And we have the attitudes for GPS, Glonass, and Galileo. So the motivation here is to combine them to achieve the improved precise point positioning. I think the method has been described clearly by Simon. And here we try two different clock weighting strategies corresponding to the weighting strategies prescribed by Salim in the orbit combination. The first one is the global weighting, which is actually the AC specific weighting. And the second one is satellite specific weighting. So we are corresponding to the IGS2 solutions. And we also applied the quaternions for the satellite attitudes. So we use the GPS and the Glonass nominal attitudes as the final attitudes for the other ACs to be aligned to, and for the GSA attitudes to use the GSA attitudes for the other ACs to align their to quaternions to this official attitudes files. And here, the impact of the satellite attitude correction is that, especially for the satellites in the eclipsing seasons, and we can see there for the Block 2A satellites in the year of 2000, if we don't have the quaternions, the different ACs will have different attitudes, and that will cause the clock discrepancy to be so large, and we can have a very good combination results. But after we apply the quaternions from different ACs, and then the jumps among the AC specific clocks can be diminished. So this is the direct impact of the attitudes correction. And then we compare the IGS1 and IGS2 combination orbit-based clock combinations. So here we use the global weighting for IGS1 orbits and the satellite specific weighting for the IGS2 orbits, just make the correct correspondence to Salim's strategies. But we use different weights for different AC and for different satellites. And that means we don't follow the value, the weighting values of Salom's warp-bit combination. And here we can see that the scale of the bars is in the unit of picoseconds. So you can see there for GPS and Galileo, the combination clock difference is quite small. The mean value is about 0.2 picoseconds and 0.3 picoseconds for GPS and Galileo satellites respectively. So, here we demonstrate that the difference between the two combination clocks based on the IGS-1 and IGS-2 warp-bits is minimal. And then in the following, we are not going to use both warp-bits to validate the PVP solutions. We use only IGS-2 to demonstrate our slides. So at first, we would like to talk about the Lexiscellar clock combination. So this is the clock computed without undifferenced ambiguity resolution. And here we show the summary results for the clock consistency among the AC specific clocks, Lexi clocks. We used IGS-2 warp-bits, and we show that in the year of 2000, the GPS satellites, we have 6 AC solutions, and the mean value for the clock consistency is about 14.2 picoseconds. But thanks to the warp-bit improvements between the AC specific warp-bits and IGS-2 combination warp-bits, you can see here the code has improved their warp-bits to be more close to the IGS-2 combination results. So then we have the improved clock consistency among the ACs, which can be reduced to 6 picoseconds. So this is thanks to the warp-bit improvement. For the Galileo satellites in the year of 2018, we have similar statistics for the clock consistency compared to the GPS statistics in the year of 2018. That is 6.9 picoseconds on average. Okay, we then try the daily GPS positioning using these combination clocks in comparison to the AC specific clocks. We don't use any quotients for facilitate cross comparison in the PPP solutions. And we show here two combination results. The first one is denoted in the blue lines, and we see that we don't use here, we don't use any quotients for the combination. The second one is red lines, where the quotients from different ACs were applied to improve the clock consistency before the combination happens. So here we see from the table, we show here, this is the statistics for about 120 stations, globally distributed stations. And we can see that for the three components, we can see the clear improvements for the east, north, and up component. The daily solution can be improved a little bit by the application of the quotients. And also we see that the combination results can produce almost the best performance for daily PVP solutions compared to the AC specific PVP solutions. Then we come to the Lexiscellar clock combination for Glonass clocks. Here, the Glonass is very special, and we see here the clock consistency among the AC, 6 AC is not so good. Its mean clock consistency is about 70 picoseconds, is quite large, especially for a few satellites which are denoted as red bars. Here we can see 3 satellites here which can harm the clock consistency among the ACs. So then we come here to make some explanation on that result. So here we show 4 ACs. The 4 top panels show the warp-bit differences from the IGS-2 warp-bits. And you see here the code and ESA warp-bits can be very close to the combination results, but the GRG and TUG results are very a little bit far from the combination results. So then in the following panel, we see there the GRG and TUG's clock combination result clocks are a little bit far from the combination clocks. So the Glonass along and cross-track warp-bit has a warp-bit discrepancy harms the clock combination for in this case. So how can we resolve it, the problem? And here we show the daily solutions using the Glonass clock in combination with the GPS clocks. We do GPS Glonass PVP solution here, and we do the float solutions. And the raw solution, if we use the GPS only solution and then we use all of the Glonass combination clocks, you can see we have similar statistics for the east and north and up components, a little bit improvement in the north and up as was demonstrated by Simon. But after we remove the satellites with large clock consistencies, I mean the bad clock consistency, which is larger than 50 picoseconds, we remove those Glonass satellites, and then we can improve the east component as well from 3.3 to 3.1 millimeters, and also a little bit of improvement in the north. So this is some kind of quality control strategy for us to remove those outlier Glonass satellites in the combination results. We can still benefit from the Glonass clock combination. And this one shows the climatic solution at one station using the GPS and Glonass data. And we also remove the R05 satellite with very large bad clock consistency with respect to the other ACs, as is shown by the blue lines in the bottom panel. Here, because of these satellites R05, the red lines in the top three panels show that the positioning accuracy is worse than those after we remove the R05 satellites. So this shows the clock consistency in the Glonass clock combination can be a good indicator for us to exclude the bad combination clocks products from the Glonass ones. All right, so finally we come to the integer cellular clock combination, which has been demonstrated by Simon in his slides. And here we just make some more examples here. And we first need to show this is the integer clock consistency. So we combine the Lexi clocks with the phase biases to form the integer clocks. And here we see that in the year of 2018, the GPS integer clock consistency can be improved by about 20% to 4.8 picoseconds. And this is also the case for the Galileo satellites to be improved to 5.4 picoseconds as well. That means the integer clock consistency among the ACs is better than the Lexi clock consistency among the ACs.
3 minutes.
And here we show the ambiguity fixing rates for both cases. So we show the attitude, the impact of attitudes. The attitude incorporating the attitudes in the combination can improve the ambiguity fixing rates as well. So we see here the ambiguity fix daily GPS and for the combination results for including the GPS and the Galileo. So we see the combination results can perform a little bit better than the other AC specific solutions after undifferenced ambiguity resolution. So then we come to the summarized results. We can show you a broad picture of the clock combination. So in the middle columns here, we show that after we do the integer clock combination, we can achieve better clock consistency among the ACs, and the Glonass clock consistency is the worst. All right, so here finally we come to the new IGS quaternion products should be applied to improve the clock consistency among the ACs. This can also benefit the positioning precision in PPP after we use the quaternions to combine the AC specific clocks. The second and the third is that we can achieve 6 picoseconds clock consistency among the AC for GPS and Galileo for the Lexi clock. But this can be improved by 20% to 5 picoseconds after we combine the Lexi clock with the phase biases for integer clocks. And finally, Glonass clock combination can still be useful if a quality control based on the Glonass clock consistency can be applied. So we can remove the outlier Glonass clock combination results to avoid any bad impact of those outliers on the PPP solutions of the users. All right, thank you. That's all I have.
Thank you very much for that really descriptive and amazing presentation. I think I have a question. It's more of a general question in regards of PPP AR. So yes, we know that constraining the atmosphere improves the PPP initialization and that solution convergence, especially in the first few minutes of processing. Is there any significant benefit in constraining the atmosphere in multi-frequency PPP for ITRF applications?
I think so. I think this is a very interesting question, but though it's not relevant with my slides. But anyway, yeah, this is very important question in the engineering applications for PPP AR. And you have the atmosphere constraint for the PPP solutions, you can certainly improve the resolution of the layer length ambiguities. And then you can achieve the ambiguity fix solution within maybe a few seconds. In the case of multi-frequency solution, we can also use the multi-frequency observations to improve the convergence efficiency. But the multi-frequency solutions cannot perform as well as the atmosphere augmented PPP solutions because we have the wide length and extra wide length solutions, wide length ambiguity resolutions, and the noise of the two combination are quite large and cannot effectively constrain the narrow length ambiguity resolution. So they but anyway, if we can combine both strategies, and then we can have the best performance for the convergence to speed up the convergences of precise point position.
Thank you for that. We have another question from Maria Virginia Macker. How do you suggest to implement the quality control in GLONASS observations?
I mean, to process the raw GLONASS observations or the GLONASS clock combination? I think if you are talking about the quality control of the GLONASS raw observations, I think there are a lot of methods. Although the GLONASS satellites have different frequencies, you can still use multiple combination observations to detect the outliers and the cycle slips. And you can also use some kind of post Arrival residuals to detect some smaller cycle slips. But if you're talking about the context, I was talking about in the slides for the GLONASS clock combination quality control, we just use the clock consistency among different ACs to identify the bad satellites, the bad GLONASS satellites with the bad combination clocks. So if you have the clock, you have the clocks from different ACs whose differences among them is so large, then you cannot have a good combination result. So in this case, you can remove them in the final combination results, and then that kind of outlier class will not impact the PPP solutions.
Okay, thank you very much for your presentation and the answers to these questions.